What if I told you the universe is about to reveal its secrets? Not in still photos, but in a time-lapse movie. This is the Vera C. Rubin Observatory, and it's about to change astronomy forever. The Vera C. Rubin Observatory is set to create the greatest movie of all time. Its mission, the legacy survey of space and time, will capture the entire southern sky in motion, night after night, for the next 10 years, using the most powerful astronomical camera ever built. National Science Foundation and the US Department of Energy started the construction of this groundbreaking observatory in 2015, with one mission that is to turn the static sky into a living timeline of the universe. After years of planning and engineering, the Rubin Observatory is now in its final phase of commissioning and is expected to begin full science operations by late 2025. The Rubin Observatory consists of three core elements: a revolutionary telescope, a camera, and a data system powerful enough to keep up with the universe itself. At the heart of the observatory is the Simony Survey Telescope, an 8.4-meter giant built for speed and scale. Its design is one of a kind, using a 3-mirror anastigmat system that delivers sharp, wide-angle images across a massive 3.5-degree field of view. That's wide enough to capture 40 full moons in a single shot. What makes it even more unique is its monolithic M1-M3 mirror. Two mirrors cast from a single piece of glass, polished for 7 years, creating a compact and ultra-stable structure. This design allows the telescope to move quickly and smoothly across the sky, able to shift its entire field of view in just 5 seconds. Paired with an advanced active optics system, the telescope constantly adjusts in real time to keep every image razor sharp, despite movement, gravity, or temperature changes. Paired with this engineering marvel is its eye, the LSST camera, the largest digital camera ever built for astronomy. Roughly the size of a small car and weighing over 3,000 kilograms, this monster camera holds a 3.2 gigapixel sensor array, made up of 189 CCDs, arranged with precision across its 64-centimeter wide focal plane. Each image it captures is so detailed you'd need 1,500 HD screens to display just one in full resolution. And despite its enormous size, it's incredibly fast. The entire sensor can be read in just 2 seconds, allowing the telescope to take a new deep sky image every 40 seconds. The camera also houses 6 massive optical filters, from near ultraviolet to near infrared, giving it the power to see the universe in full color across a wide spectrum of light. The telescope and the camera working in sync will take high-resolution images of billions of stars, galaxies, and cosmic events. Then it will carefully put all these images together like frames of a giant time-lapse to show us how the universe actually moves and changes. We'll be able to watch stars explode, galaxies drift apart, asteroids race through space, and mysterious objects suddenly appear or disappear. For the first time, we won't just look at the universe, we'll watch it happen. Over the next decade, the legacy survey of space and time will scan the entire southern sky, revisiting every patch roughly 825 times. Each visit adds another frame to the story, another moment in cosmic history. With each 15-second exposure, it can detect objects as faint as magnitude 24.5. And when all those exposures are stacked together, Rubin pushes the boundaries to magnitude 27.5, exposing some of the faintest galaxies and farthest structures ever seen. Every object will have its own light curve, like a personal timeline. From faint galaxies at the edge of the observable universe to fast-moving asteroids in our solar system, Rubin will record how each one brightens, dims, flares, or vanishes. These light curves are more than just data points, they're stories. They tell us when a star pulses, when a black hole devours, when something new suddenly bursts into view, and Rubin will collect billions of them. So, what will we discover when we watch the universe in motion? The Rubin Observatory wasn't just built to look, it was built to reveal. And it's targeting the 4 biggest mysteries in modern astronomy. First, the invisible scaffolding of the universe, dark matter, and dark energy. Rubin will map the shapes of billions of galaxies using the subtle warping of their light, called gravitational lensing, to trace where dark matter hides. And as the universe expands, Rubin will track how fast that expansion is changing, giving us new clues about the mysterious force known as dark energy. Next, the solar system. Rubin is expected to discover millions of asteroids and comets, including those that may pose a threat to Earth. It's even designed to spot interstellar visitors, objects like Oumuamua or Borisov, drifting through our system from distant stars. In fact, in just 10 hours of early testing, Rubin discovered over 2,000 new asteroids. The third thing it will focus on is the transient sky, the unpredictable, explosive, and unknown. Rubin will detect around 10 million changes every single night. That's everything from supernova, kilonova, and neutron star collisions to flashes we don't even have names for yet. It will be the world's most powerful alert system for cosmic events, issuing warnings within 60 seconds of detection. So telescopes around the world and in space can swing into action. And the final objective of this mission is the Milky Way. Rubin will chart its stars in incredible detail, uncovering faint stellar streams, dwarf galaxies, and evidence of ancient galactic collisions. It's archaeology on a cosmic scale, piecing together the Milky Way's history through the scattered remains of what it consumed. But with all these discoveries comes a problem. Rubin will generate 20 terabytes of data every single night. Over 10 years, that's 500 petabytes. More than all the written content in human history. No human can possibly sift through that, not even an army of them. So Rubin brings in a new kind of astronomer, AI. From the moment its 3.2 gigapixel camera snaps an image, within 60 seconds, Rubin's system detects if anything has changed, a flicker, a movement, a sudden flare. If it has, an alert is triggered and sent to astronomers around the globe. That alert contains predictions made by machine learning models trained to recognize patterns in light curves. In June 2025, Rubin released its first ever images, and they're breathtaking. Captured during testing, these images show vast regions of the night sky in extraordinary detail. Entire star clusters, distant galaxies, and faint cosmic structures all revealed in a single frame. So imagine what happens when this isn't just one image, but thousands, taken every night for 10 straight years. Every time we've opened a new window to the universe, something extraordinary has looked back. We weren't expecting black holes. We didn't plan for dark matter. And exoplanets, those were science fiction, until we found thousands. Now, with Rubin watching the entire sky night after night in more detail than ever before, we're opening the widest window we've ever built, and what we find may change everything.